Good afternoon, everybody. My name is Zhi, and I'm now a master student, but I will get my master degree this month from Xi'an Jiaotong University. And my topic is about the energy storage market power withholding bonds in real-time markets. This year, there has been an exponential increase of the energy storage capacity. And according to the CAISO's report last year, the energy storage capacity has reached 5 gigawatts, which makes up for over 7.6% of the total nameplate capacity. And because of the fast response speed of the energy storage, frequency regulation can be one of the main applications for the energy storage. But nowadays, the regulation market is relatively shallow compared with the increasing energy storage capacity. So the focus of some energy storage operators may be shifting towards the energy market, and they may gain their benefits through the price arbitrage. That means they may charge when the price is low, and they may discharge when the price is high. And then with such a great share, it is much more important for us to pay more attention to the influence of energy storage to the market dynamics. And one of the situations that the market operators hope to forbid is that the participants may want to exercise their market power. They may want to alter the prices away from competitive levels to gain more benefits. And in the past, the electricity market is established mainly based on the rules for the thermal generators. But for the traditional thermal generators, they mainly exercise their market power through the capacity withholding and economic withholding. They may bid higher than their marginal cost. The cost for the thermal generators can be fixed to some extent, like their fuel cost. Their bid just depends on the generation power, or at least they have nothing to do with the real-time price, and they don't want to exercise their market power. But the story will be much more complex and challenging when we think about the energy storage, because for the energy storage, they gain benefits by arbitrage the market price fluctuations. This means they will face a unique opportunity cost. When the energy storage decides to charge at the peak price, they may lose the opportunity to get more benefits at the future lower price. So for the energy storage, they have to bid according to the opportunity cost. That means they have to care more about the real-time price, the prediction of the real-time price. But furthermore, their prediction cannot be totally precise. That means when we consider the uncertainty of the real-time price, the bids will be more complex. About these two situations will be reasonable for the energy storage to bid. However, some energy storage may also want to exercise their market power. And in this work, we hope to analyze the economic withholding behavior out of different considerations. In details, some energy storage will just bid according the opportunity cost and the price uncertainty, but other energy storage may hope to exercise their market power. Firstly, let me forget about the market power. Firstly, we will build the energy storage arbitrage model. Here, we build it as a multi-interval problem for energy storage. They hope to maximize their overall revenues during maybe 24 hours, including the discharge and charge revenue and discharge cost and terminal SOC value function. And we consider several constraints like power rating, energy rating, and the energy storage cannot charge and discharge at the same time, and the SOC evolution between two time slots with its efficiency. And then we transform the multi-interval problem into a single interval problem using the dynamic programming. with the SOC value function at each time period. This SOC value function reflects the opportunity value of the remaining SOC at the end of each time period. Let me talk about the market power. Because we hope to consider the influence of energy storage on the real-time price. So here we establish a market relationship between the storage operation PT, BT, and the real-time price lambda T here. Here we just build an aggregated continuous function H, but we will not give the specific formulation of the H function. But here we just give three characteristics of the function H. The first is the function H must be 0 at its origin. It means that when the storage will not charge and discharge, then the price will keep the same will keep the uninfluenced situation. And second is the HX must be decreasing. It means the charging operation will increase the real-time price. And the third one is the XHX must be concave. This is to enable the arbitrage problem above to be a convex problem. That is to simplify our discussion for the following. Yeah. And after defining the price sensitivity model, here we give two other definition. One is a price maker and another is price taker. The price taker or the price maker refers to the storage who want to exercise their market power while bidding. So for them, in its arbitrage model, the price maker will use the price sensitivity model. And for the price taker, they will not exercise market power while bidding, because, like they will not assume that they will have the influence on the real-time price. So it will just use the basic real-time price lambda T in its arbitrage model. And then they can just bid according to the single interval problem. And here it can bid. We can calculating the charging bids and discharging bids by through the marginal operation cost. The C here, and we can see that the charging bids and discharging bids is a function of the VT. What is VT? VT is the marginal, the big VT is our SOC value function, and the small VT is the derivative. It's the marginal value function here. And then when we hope to discuss the difference between the bids of price maker and price taker, then we find that the difference of the bids is linear to the difference in their marginal value function. So in our following discussion, we will just talk about the marginal value function instead of talking about the bids. And then here I will firstly give our main results of the market power economic withholding bound. It tells us that the upper bound of the difference between the marginal value function of price maker and price taker is determined by the expected future peak price and expected current price. When we model the price uncertainty as a time-varying single-wise independent process. Here I want to highlight 2 points of our main result. The first is distribution free. This bound only depends on the expected price, regardless of the distribution of the price uncertainty model. And the second is model free. Although we have built the aggregated price sensitivity model H, but this bound holds regardless of the function H. And to prove our main results, here we discussed 2 cases. The first case is considering a deterministic price model. And the second case, we will consider the price uncertainty and build a stochastic model. And in both cases, we will first calculate the marginal value function for both price maker and price taker. And then we will try to analyze the differential between price maker and price taker and try to relax the upper bound of the differential. And first is the deterministic price model. Here we use the dynamic programming method to calculate the marginal value function on our recursive framework. When given the marginal value function at time period t, then we can calculate the marginal value function at t minus 1 according to the relationship between the marginal value function and the real-time price. I think that it is a little complex, so we can have give a much more direct explanation. At the formulation of marginal value function, it includes 5 cases, which means when the price is quite low, the energy storage will decide to fully charge, and when the price increased, then the storage may decide to partially charge or just keep its energy. And when the price increased to a relatively high level, then the storage will decide to partially discharge or fully discharge. And when we compare the price maker and price taker, we can see that picture. Assuming that the marginal value function for price maker and price taker at time period t keeps the same, like the black line, and then we have a fixed price lambda t here. Then we can calculate the line for the price maker and price taker at time period t minus 1. We can see that the gap happens when the price maker decides to partially charge or partially discharge. And to do some relaxation, we introduce the maximum differential of a variable of the marginal value function, the theta t here. And then if we assume that at time period t, we have the theta t as the maximum differential, then we can calculate theta t minus 1 in a similarly recursive way, which is really similar to the formulation of marginal value function. And based on the formulation of theta t and the marginal value function, we can get our upper bound of the market power economic withholding. And under a deterministic price model, this upper bound is based on the future peak price and the current price. And then we hope to extend our model to consider the price uncertainty. We use a stochastic dynamic programming method to calculate we firstly calculate the marginal value function based on the probability distribution of the real-time price. And then similarly, we can get the formulation of our maximum differential variable theta t here. And based on these two formulations, we can get our final results under the stochastic price model, that the upper bound is based on the expected future peak price and the expected current price. And this result can be a little interesting and realistic, because in many papers we may assume that the expected real-time price can be just the day-ahead price. So although our situations is in the real-time market, but we can just use the day-ahead price to formulate our final result, and it can be applied in the real-time price in the real-time market. And here is our simulation part. We verify our models based on the real-time price from New York ISO, and we use a 2-hour duration battery with 90% efficiency. And we consider 3 scenarios. The first is the price taker one. They will not exercise their market power while bidding. And second and third is the price taker one with different specific price sensitivity model. Because in our formulation, we just use an aggregated one. And in our simulation part, we will use some specific sensitivity model. The first is linear model, and the second is cubic model. Here, firstly, we give the storage arbitrage process. We can see that sometimes when the price taker decides to fully charge, and then the price maker will conduct more withholding, they may decides to partially charge. And then we we verify our marginal value function for both the price taker and price maker using the different price sensitivity model and get our upper bound and the real gap. Yeah, the right picture shows the upper bound theta t and the real gap between the price maker and price taker. We can see at least the upper bound is always bigger than the real gap. And although maybe our relaxation is not a perfect one, but at least it is correct. Yeah. And furthermore, we conduct some sensitivity analysis under the linear price sensitivity model. We test different linear parameters. The alpha here, as the parameter alpha increase, the storage tends to conduct more withholding, which is very intuitive, I think. And then we also test when there exists a gap between the actual price parameters and the predicted price sensitivity for the price maker. In the right pictures, then the price maker will not gain as much revenue as expected because of this gap existing. And the price maker will gain the most revenue when both the predicted price sensitivity and the actual price sensitivity equals to 0, which means the storage operation will not influence the real-time price, and the price maker is aware of such kind of fact. And the picture shows a form of a ridge, which means with a fixed predicted price sensitivity, or with a fixed actual price sensitivity, the price maker will gain the maximized revenues when it has a perfect quantification of its market power. And in conclusion, we proposed an analytical storage market power examination framework through the dynamic programming. And by comparing the bids made with and without excising market power, we introduced the upper bound of economic withholding caused by market power, which is model-free and distribution-free. And in our future work, we may consider more about the price models. Maybe we can consider the intertemporal price models, or consider more about the ramping rate caused by the terminal generators. And although our results may be some kind of interesting, but whether it can give us more ideas about assessing market power for storage is still need further consideration. And thank you for my advisors and other collaborators. And thank you, Columbia University and Xi'an Jiao Tong University. And any questions?